In the introduction video, we saw a 1,000-foot overview of the theory of incomplete measurements, a proposal to unify the theory of general relativity and quantum mechanics. In particular, we saw that the theory could be summarized in 5 key points. In the previous video, we defined what measurements are. In this video, we will focus on the second point, namely that measurements are all discrete. We will see that as a result, we can conclude that there is no continuum, no space and no time. But first, we must clarify what we mean by discrete. When we say that measurements are discrete, we mean that every single instrument always delivers a finite number of possible results. In other words, we use discrete here as opposed to continuous. Some of us may have trouble with this idea. The world around us appears continuous. But this is actually an illusion. We simply have very little awareness of the limitations of our own senses. Modern life made this patently obvious. We are all familiar with smartphones and computers. The pictures and sound they deliver feel perfectly normal to us, continuous and fluid. Yet we know, literally by construction, that this requires a very limited number of pixels, a small number of images per second, and digitized sound. We simply can't perceive individual pixels, gaps between images, or individual sound samples, despite knowing for certain they are there. We are not talking about very large numbers either. CD quality sound only requires about 44,000 16-bit samples per second. Movies appear very fluid with only 60 images per second. Apple's so-called Retina display, exceeding our ability to see the pixels, only requires about 100 pixels per centimeter. This is also true of measuring instruments. When we measure a length, using for example a good old tape measure, there is only a small number of tick marks. In most of the world, the smallest unit for daily measurements is the millimeter. So a 5 meters tape measure can give me only about 5,000 distinct results. Of course, we know that there are smaller units, like the micron. And since we see a gap between the tick marks on the tape measure, it is easy to imagine that we could measure microns with it. But this is false. When we measure 15 millimeters, this does not mean that we are measuring 15,000 microns. Values such as 15,013 microns are just as likely. The opposite is true too. We cannot use a tape measure to reliably estimate the distance between two cities in millimeters. We can state with some certainty that the distance between Moscow and New York is around 7,530 kilometers. Giving a distance with a 1 kilometer accuracy, however, is already a matter of conventions, since each of the two cities is more than 20 kilometer in size. Do you measure the distance between the closest edges, or from city hall to city hall? So measuring such a distance with millimeter accuracy is a physical nonsense. To the best of our knowledge, the discrete nature of measurements extends all the way down, and all the way up. On the way down, we will reach atoms. This picture shows individual atoms measured by an electron microscope. We also know about even smaller particles like electrons or protons, although we cannot image them directly yet. On the way up, we see discrete units such as stars or galaxies, which are well identifiable in interstellar space. Things that may look more continuous, like gas clouds, are really made of discrete components. This allows us to make sense of what we observe. Why does it matter? Let us illustrate with a counterexample. What you see here is a field of stars at the top of the screen, and continuous random noise at the bottom. Now let's move the two pictures with the exact same movement. The discrete elements in the top picture are what allows us to detect the movement. By contrast, a picture without such discrete elements does not allow us to reliably detect the direction or amplitude of movement. The same is true with movements in any direction, including time. In short, discontinuity is essential for physics, at large scale just like at small scale. Discontinuity is what allows us to make sense of the universe around us. Let us apply these observations to measurements of space and time. Like other measurements, instruments used to measure space and time always provide discrete results. There are no continuous measurements of space, no continuous measurement of time. So why do we keep talking about the spacetime continuum, when there is just no observable continuum? One reason is that continuity is actually a very neat mathematical simplification. When we think about distance, for example, irrational numbers pop up even in the simplest reasonings. We find them in the most common geometrical figures, like squares or circles. The length of the diagonal of a square with a side of 1 is the square root of 2. The Pythagorean theorem tells us that the circumference of a circle with diameter 1 has length pi. We have a video with more details on this topic. For now, suffice to say that neither the square root of 2, nor the number pi, are rational numbers. In other words, they are not the ratio between two natural numbers. The case of the square was actually known to ancient Greeks, and this observation was a real problem for their philosophers. In order to properly deal with irrational numbers, you need continuous mathematics, something that mathematicians call real numbers. This is a relatively recent invention, about 2 centuries old. Now, if irrational numbers show up in such simple geometrical figures, and if having irrational numbers require continuity, doesn't it naturally follow that space and time themselves are continuous? That's essentially what Newton argued in the Scholium of the Definitions chapter of his famous Principia. What Newton suggested back then was, if you are interested in the movement of a ball over a football field, what actually matters is what remains when you remove the ball and the football field. What remains is a continuous, simple space and time that the physicist can easily reason with. Newton calls it true, absolute space and time, as opposed to the vulgar, relative notion of space and time measured by clocks or rods. As a result, Newton's second law of motion uses continuous mathematics, not vulgar measurements. The acceleration in this equation is the second derivative of the position x over the time t. Newton never tells us how to measure any of these quantities because they are all supposed to be well defined. They are supposed to be real, to be the true value. In other words, in Newton's view of the universe, a variable like x is the true position, and any measurement of x is only a vulgar approximation of that true reality. All physicists have followed in Newton's footsteps since then. In quantum mechanics, Schrödinger's equation uses the exact same idea of space and time, with continuous variables still called x and t like before, supposed to represent a single space and time that is identical irrespective of how you measure it. We will see in other videos many of the problems that this idea causes. Einstein too borrowed this idea when he talked about the spacetime continuum, popularizing the word continuum for generations of Star Trek fans. Actually, Einstein identified that he needed a bit more than just continuity. He needed real functions that he could differentiate twice along their variables, something that he called the Gaussian hypothesis. What you see on the screen is chapter 25 of his 1920 book on relativity, discussing this very topic. It is a bit ironic for Star Trek fans that, if the theory presented in our videos is correct, the notion of continuum will be obsolete in the 24th century, having joined luminiferous ether and spontaneous generation in the dustbins of science history. As you probably heard, Einstein added a little bit of relativity back into the picture. In Einstein's views, there are now multiple ways to measure distance or durations, based on the speed of the observer. Consequently, it becomes necessary to specify the reference frame. However, as a whole, we still have the infamous spacetime continuum. It may be dynamic and curved in the case of general relativity, and we may need to slice it in different ways depending on the observer, but it's still the same universal background as in Newton's or Schrödinger's equation. The theory of incomplete measurements suggests that we take the exact opposite approach. Measurements come first, and they are all discrete. This is true even for space and time. But, when we talk about space and time measurements, what are we really talking about? The modern definition of the meter and second give us an interesting clue. The second is defined in relation to the time it takes to emit a particular kind of photon. And the meter is defined in relation to the length traveled by light in some given duration. In other words, our modern definition of space and time suggests that they are fundamentally properties of photons. We will explore this more in depth in a follow-up video. For now, let's just say that just like there is no continuum in the theory of incomplete measurements, there is also no space and no time, only measurements of space and time, which are not considered identical or equivalent. The continuum is only a useful approximation to smooth out the differences between physical measurement processes. We need the continuum to easily relate processes that work at different scales or use completely different physical principles. Typically, this involves a fair number of calibrations. Relating distinct measurements without resorting to the continuum approximation requires a new principle of relativity, and as a consequence, a new way to relate measurements to one another. These relations will be the topic of the next video.